Much, Hila. So the next talk is on higher order effectful programs by Andrew Hirsch. Stage is yours.
All right. So I'm not going to be as how to listen to a talk as Hila was, although that was really wonderful to actually get to hear. I'm going to talk to you about higher order effectful programs, which is a much bigger class of papers that you'll get to hear about both in the session and in general. So I really want to focus on what are these effect things anyway, and what do we mean by higher order programs, and how does that make things challenging? And then I'll talk a little bit about the papers you're going to see in the session today. So we're probably used to seeing mathematical functions described as machines that take in input and produce output. And mathematical functions are just completely determined by this input-output behavior. You give an input, you get an output, that's what the function is, there's nothing more. But programs are a little bit different. You give them an input, and they do things like take time, or print to the screen, or produce many possible results. Maybe they just choose one thing from some set. These are the effectful things that we have to deal with. This intentional behavior matters for programs. Now, of course, this gets really hard when you have a program that takes a program as input. And that program might have some effects. And now you have questions like, does Pete print to the screen? How often? What? These questions are really hard, and that is the sort of questions that the papers in this section all try to answer. And there's a lot of different ways of attacking this problem, and we're actually going to see a huge variety of methods come up in the session today. So I just want to briefly, in the last half of my talk, get to talk about a little bit of how each one of these papers is going to tackle that problem and think about something different. One thing I want to point out that I didn't put on the slide, sadly, they're all trying to be generic. So they're not talking about printing to the screen, they're talking about any effect like printing to the screen, which of course makes the job in some ways a lot harder, but also a lot more exciting. So the first paper we're going to see is on model checking higher order effectful programs. And the session title is right in the name, so you know it's going to be good. I looked at this paper and I said, okay, what is model checking and what's going on here that's going to be hard? And model checking is just the question, okay, I want to know if some specification is true of some program. How do I do that? Well, I build some mathematical model of the program, usually some sort of graph structure, although not always. And then I ask the question about that graph. This works really well for pure things like lambda calculus, but when you have effects, you get really mixed results depending on the effect that you have. So what this paper does that's really cool is use the idea of algebraic effects and handlers, which I don't get time to talk to you about today, sadly, but are a really cool technique in effect theory, to study this problem in general for any effectful program. And the main result is that if your handlers have a simple syntactic restriction, they can actually get a model checking program to work for any handler that satisfies that program. The second paper is about this new language, REML, that has explicit effects and effect constraints. And REML is really concerned, to some degree, with parallel programs. And if you think about parallel programs that write to memory, if you have two programs writing and reading from two separate parts of memory, like everything's good, life is easy, you can just run them in parallel. But the moment they start doing some stuff in the middle that they both have to deal with, like life gets a lot harder. And you have to do a lot of explicit reasoning about, like, am I allowed to touch this part of memory right now? Is somebody else holding it? Am I going to be trampling on it? So how do you tell whether these two programs are going to overlap at all? Well, there's something called region analysis, which is a type of effect analysis that they do. But what about other effects? What this paper does is actually combines region analysis, which is a very complicated form of effect analysis, with a more general effect analysis called type and effect systems, to try to do both at once. DCAF is the third paper. It's a directed effectful cost-aware logical framework. So here we're going to get to kind of much more complicated languages rather than complicated things we can do to languages. We're going to talk about type theory. And I'm not sure how many of you are aware. In type theory, there's generally 4 judgments we have to worry about. A program has a type, a program is a type, 2 programs are equal at a type, or 2 programs are equal as types. And the big insight of this paper is to take this notion of, E is equal to E prime as a member of A, and say, well, usually that was extensional, i.e. we only can care about the input-output behavior. In their previous work, the same authors said, well, what about the cost? We also want to reason about cost here. And they got some stuff to work, but it didn't take care of any other effects other than just cost. What their insight is in this work is, hey, instead of equal, let's say that one program is less than another. You could think of this as like produces strictly fewer traces, or has fewer possible results. And with this, they're able to actually make their framework work for a whole swath of other effects. Finally, we get to the distinguished paper of our session, Modular Denotational Semantics for Effects with Guarded Interaction Trees. Okay, so what are interaction trees, first of all? So interaction trees are a way of dealing with embeddings of languages into Coq to build models. Usually you have 2 options, a deep embedding with some sort of step relation, big step, small step. There's a lot of repeated work you do with this. It's very non-modular. Doing a lot of work over and over again to build these models. Another option is to use a shallow embedding into Galeno programs, and that works great as long as you don't have any effects, all your programs terminate, which is kind of sad. The iTrees framework, interaction trees, is a framework designed to address this problem. And iTrees look kind of like this, and I'm not going to go into a lot of detail, but they give you this way of building these infinite trees of interactions with an environment to represent and model effects. And they work really, really well as long as you don't have any higher order computation at all, which is obviously a shame. What this paper does is use guarded type theory and ideas from domain theory to extend these interaction trees with higher order functions. I'm afraid that's all I have time to tell you about. There's a lot of really cool detail in all these papers. I really highly encourage you to come to the session and see all the amazing work that these authors have done.